Hey folks, welcome to the video. In this video we're going to be talking about the parallel axis theorem. It's a way to calculate the moment of inertia of an object through an axis that's not through its center of mass. Let's get into it.
So last time we discussed moments of inertia, and we saw how to calculate the moment of inertia through a certain axis for an object. We wrote down that I is equal to the integral over dm times r squared, where we have some object, say it has total mass m, some origin, and what we're doing is we're taking these tiny little submasses, dm, at some distance r, and we're integrating over each one of these masses at each of these distances, and that gives us the moment of inertia of an object. We also saw last time that we had an example, and the example we saw was that it was a solid cylinder with a uniform mass density. And we found that for the solid cylinder of uniform mass density, through an axis that goes through its center, like so, that moment of inertia was equal to 1/2 ma squared, where a is the radius of the cylinder. And now a question arises. Well, what happens if we want to calculate the moment of inertia of the cylinder if the axis were instead over here? We were rotating the cylinder about its edge. Well, if we think about it, we would say, okay, if we were to rotate the cylinder about its edge instead of its center, it would be harder to do so. It would take more effort. So intuitively, we would think that the moment of inertia should increase. In fact, the moment of inertia to rotate an object about an axis that doesn't pass through its center of mass is higher than rotating it about an axis through its center of mass. So let's actually see how higher it is. So what we're going to do is we're going to say, okay, we have this mass, call it big M, and it has center of mass located there. Let's say it's right there. And the center of mass, so let's say that the origin is at the center of mass. So that means the distance of the center of mass from the origin is 0. And in this case, let's say that the center of mass has the following moment of inertia, I sub cm. And now let's say we wanted to calculate the moment of inertia for this object through an axis that passes through this point right here. We'll call this point, so this is a new origin, and we'll say that this point is located at a distance, let's call it vector a. Okay, so it's located at a distance vector a, and our question is, what is I, the moment of inertia, for the mass m with axis of rotation through vector A. Now, let's see. We'll write down that I is equal to dm, and now we note that the axis has shifted. So instead of writing just simply r squared, we would instead have r vector minus a quantity squared. It's because we've shifted the axis of rotation. The origin is still at the center of mass, but because we've shifted the axis of rotation, our expression for r squared must also shift to r minus a, the quantity squared. So that's the moment of inertia through this axis. Let's carry out this integral. We get that this is equal to dm of r squared minus 2 r vector dot product with a vector plus a squared. Okay, let's split this as such. And we notice that this quantity here, that's ICM from before. Because a is a constant, this integral just gives us m times a squared. And this one, this integral, actually gives us 0. Let's see why that's the case. So we have the integral of dm r dot a. Okay, so we can write this as the integral of dm r dot a vector. This is because a here is a constant, so we can take the vector a outside the integral, evaluate this integral over r, and then dot product it with the vector a. Okay, so the question becomes, what's this quantity? Well, the integral of r over dm over mass is nothing but the total mass times the center of mass position. That's because the center of mass is given by the expression integral of dm r divided by the total mass. It's a weighted average of each of the points, each of the submasses in this continuous mass. So we note that because RCM is 0, because the center of mass is the origin in this problem, this quantity is also 0. In particular, it's the 0 vector. So we get that this is equal to 0 dot a, and that's just 0. So this checks out. Okay, so let's write it down. I is equal to ICM plus m a squared minus 0. And that's the moment of inertia of this object through an axis that is distance a away from the center of mass. And we call this the parallel axis theorem. The reason is because if we were to take the axis passing through the center of mass and then shift it, keeping it parallel to the center of mass axis, if we were to shift that axis, then we would get the following moment of inertia. Okay, so back to our example of the cylinder. We had that for the cylinder, if you had it's a uniform cylinder and you have its center of mass axis being this green one, we know that the center of mass moment of inertia is 1/2 ma squared, where a is the radius of the cylinder. And if we wanted the moment of inertia through an axis that passes through its edge, then that is equal to ICM plus m a squared. So that's just 1/2 ma squared plus ma squared. So we get it that it's 3/2 ma squared.
I hope you all found that interesting. If you did, like and subscribe. Thanks so much for watching. I'll see you guys next time.